Good morning and welcome to day 3 of the 234th American Astronomical Society meeting here in St. Louis, Missouri. I'm Rick Fienberg, press officer for the AAS. Assisting me today by monitoring our webcast is the press officer of the Solar Physics Division, Trey Winter, and Susanna Kohler from the editor of AAS Nova will be helping during the Q&A as well by handling our microphone. Please silence your cell phones if you have a phone on you. There's at least 2 releases going out about this morning's briefing and possibly a third. They haven't gone out yet, but they'll go out within the hour. And yesterday, I've posted the videos from yesterday's briefings on our archived webcast page, so you can get to those, and I've also linked to the presentation files. So if you need to get access to those, those are available on the AAS 234 press kit. So in case this is your first press briefing at a AAS meeting, the way we do it is I'll introduce all the speakers and the topics they're going to cover, and then they're going to give their presentations one right after the other. So hold your questions until the end, and then we'll do Q&A both here in the room and for the journalists who are tuned in from the remote webcast. So if you've been paying attention to the briefings since Monday, we've already had 2 briefings that have included results on solar physics. That's not surprising at this meeting because we're meeting with our Solar Physics Division. That's in part why Trey is here. We also yesterday had an entire briefing on the Milky Way and spiral structure in galaxies. Today, we have a briefing that has more results about the Sun and more results about the Milky Way galaxy. We have 4 presentations this morning. The first 2 will be about the Sun. The first one is predicting the end of Sunspot cycle 24, that's the current one, and its effects on Earth. That'll be by Robert Leamon from the University of Maryland and NASA's Goddard Space Flight Center. Then Irina Kitiashvili from NASA Ames will speak on solar activity forecasts for the next decade. Then we'll switch from the Sun to the Milky Way. We'll start with Grace Wolf-Chase from Adler Planetarium, asking why do massive and not so massive stars form in the Milky Way? And then, last but not least, Sukanya Chakrabarti from the Rochester Institute of Technology will describe Antlia 2, the Dark Dwarf Galaxy that crashed into the Milky Way. And so let us get started with Bob Leamon.
Right, thank you, Rick. My name is Bob Leamon, and I am currently at the University of Maryland. I sit at Goddard, but perhaps it's relevant here is the fact that I spent 5.5 years at NASA headquarters. And I went to headquarters as a solar and solar wind physicist, and I came back having done a whole bunch of bureaucratic and managerial stuff for the magnetosphere and the ionosphere and the atmosphere and sun climate as well, which is what got me started on some of the things we're going to talk about today. So this was talking about my iPoster this morning. That's going exceedingly well. I love the format. I would encourage everybody to consider it. And moving on, so let's get the big picture, the why, what, so what out of the way first, and then we'll get to how we came to it. So I'm going to talk about the solar cycle and its impact on the El Nino Southern Oscillation. And people have tried to do this for years and said there's some correlation. No, there's not a correlation. But the trick here is not think of the solar cycle in solar max or solar min, but rather when does the interaction between the various magnetic flux systems on the disk and the solar flux system corresponding to cycle 24 will terminate, and I say terminate because it happens really abruptly. The magnetic flux cancels at the equator next year, or at least that's our current prediction from 9 to 12 months from now. And when this happens, you see a sudden surge in activity of the next cycle at mid-latitudes, and with it comes a cosmic change in the amount of cosmic rays impacting the Earth, and a swing from El Nino to La Nina. So we're in an El Nino condition right now. We've probably heard enough things on catastrophic weather of late, and all the various things going on, certainly flooding around here, comes from the somewhat standing weather patterns that set up in solar minimum when we have an El Nino. So the big so what here, of course, is that if we can predict something, then we can take mitigating processes, and we're quite talking literally billion dollar issues here. So I'm not going to make a prediction about how strong the El Nino will be this year or how strong the La Nina will be next year, but I will say that there will be a swing from one to the other. So we're now going to get to some graphs. So I said, don't smooth the data. Don't look at just a up and down, a sinusoid or solar max or solar min. The magic comes from looking at the interaction between the bands of one magnetic flux system and the other. So this is the bottom panel of this graph combines data from SOHO and SDO, NASA ESA NASA SOHO and NASA SDO. So when SOHO launched in Christmas 1995, so that's when this data starts. And you can actually track the small-scale magnetic features for each of the 4 cycles since then. Cycle 22 terminated in 97, so just after the start of that. And what I mean, terminators, each hemisphere has opposite magnetic polarity, and each cycle in each hemisphere has alternating polarity. So evens have one polarity, odds have the other, and magnetic flux, opposite magnetic flux, tends to attract and cancel. So that cancellation at the equator of the old cycle flux leads to a sudden step increase, rapid increase in the sunspot number, and in the middle panel and the top panel, the F10.7 radio flux, which is another solar activity proxy. And this is a really sharp transition. It happens less than 27 days, less than one solar rotation. And we see changes in just about every variable we care to look at. You can see it also in various EUV hot solar corona emission lines. You can see it in the number of flares and CMEs that the sun gives off. And the big change is the cosmic rays. So as the number of active regions on the disk changes, that it changes the global large-scale coronal field enough, and which changes the heliospheric field, leading to a drop in cosmic rays. So the cosmic rays is anti-correlated with the solar cycle. The simpler the system is, the more cosmic rays come in and hit Earth, and the more stuff that's out there, CMEs and ejector and the such like, means it drops. So here's the money figure from the presentation. So the magic trip here is this is a so-called superposed epoch analysis, which is a common technique, but rather than doing it in terms of time, there's not 11 years across the bottom here. You do it in terms of scale, of fraction of a solar cycle from one terminator to the next. And I have to say that this, if anyone uses Garmin running watches, but this whole thing came out of the fact of when I was training for an Ironman 2017 and using the software that don't think in terms of time, because as you get tired, you go slower, but you still go around the loop is the same distance. So rather than doing it in terms of time, I did it in terms of distance or fraction of a cycle, and then this very coherent pattern comes out. So while the solar cycles, we say it's 11 years, it's 11-ish years. The last one was almost 14. They vary somewhat. The big pattern here is that you see at these terminators at 0 So the graph goes from minus a quarter to 1/4. So it's 1.5 cycles overlapping, just so that the fun stuff doesn't happen at the edge. And you see at this terminator, you see the drop in cosmic ray flux, which is the GCR, the bottom but one panel, an increase in F10.7 that I talked about before. Then you see but the bigger increase in F10.7 doesn't happen until later. And then the ENSO panel, you see this coherent jump from flip from El Nino to La Nina. And the fact that that step in F10.7 happened, the big step in F10.7 happens later, implies that it's particles rather than photons that are driving it. So we have some big picture real world implications of this. I mean, it's fairly well understood that Atlantic hurricane season is bad the first year of a La Nina after an El Nino because of how the warm waters and upper level winds blow. But hey, now that we can say when one of these is going to be, so I can say that 2020 is going to be a bad Atlantic hurricane season. And again, simple economic supply and demand issues say that things grow well in the U.S. during El Nino conditions. La Nina, not so much a simple supply and demand. You see a shock, a jump in like corn and wheat prices. And perhaps not unsurprisingly, because we're in an El Nino, chances are that 2019 will be the warmest year on record, and 2020 will be less so. So moving on quickly, and say that why am I confident that it will happen in April 2020? I can do it by tracking the progression of those bands. I showed this one way, and this other neat technique called the Hilbert transform, which is a signal processing electrical engineering technique that kind of measures how fast things move. And simply by extrapolating the curve out from the little inset in the right-hand side there, this straight line, I just extrapolate that out to mid-2020. So quickly, I can actually I'll skip that. Moving on because really, we're talking about sun and climate. People are going to say, "Oh, climate change," but it's not man-made global warming, it's just the sun. But really, this whole thing works because we have global warming. Because we have a warming troposphere, it means that we have a cooler stratosphere. Just imagine you put a blanket on yourself if you're cold at night. You stay warm under the blanket, but now your room gets slightly colder. And because we have a colder stratosphere, couples the upper atmosphere and lower atmosphere, making the atmosphere more susceptible to the punch or anti-punch, if you will, of fewer cosmic rays, and that changing the atmospheric conductivity and reducing thunderstorms and shifting cloud patterns across the equator, across the Pacific. So I think I touched already on all the various things about recent extreme weather reports. There's always this low pressure system called the Aleutian Low off Alaska that tends to be stronger and remain static during solar min El Nino, which controls the jet stream patterns across the United States, which is why we have what it is. So really, it's cosmic rays, which most modern climates tend not to accurately include, is the likely coupling mechanism for solar activity changes. And I know I'm eating time here, so I do have to say that there was some press buzz last week, the week before, on this paper about Jupiter's tidal dynamo, which while yes they may explain the sunspot cycle, there's more to it than that. The sunspot cycle is more than 11 years. It's considerable variance, as I talked about. It goes from 8 to 14 years, and it's the magnetic activity cycle that has nothing to do with Newtonian dynamics at all. I have to say that they actually quoted our previous paper on this subject. They need more than just Jupiter. So in summary, our model of terminators can simultaneously explain solar cycle timing, as to where max and min, see the sudden onset activity of the terminator, implications for El Nino that I talked about, and if you go through the poster, I didn't talk about today, I can tell you why the last cycle was unusually long. So thank you very much for your time, and I look forward to fielding questions in a few minutes. Thank you.
Good morning, and in this presentation I would like describe briefly most recent study for prediction long-term solar activity. And the question is why we so care about this why we so care about this. First, we know what sun is the most important star in our life. It is not because provides some heat, light, but also, especially with the current development of technologies, we became more and more sensitive to space weather conditions, disturbances from the sun. And in addition to this, because we have plans go to Moon, Mars, and maybe in future to another planets, effects related to solar activity became extremely important in terms of we would like make plans of very far ahead to take into account the possible extreme conditions. And on this chart, you see a number of different missions on different stage of operations, which attempt to study conditions in different layers, from subsurface layers to heliosphere. For example, one of operating currently mission is Solar Dynamics Observatory. One of goals of this mission is provide full disk high-resolution observations, which help us to understand global dynamics of the sun, and in particular, evolution of magnetic fields. But of course, because importance of the sun, we have very long records of observations, which start in very, very early days. And on this chart, you see sunspot number variations for 400 years, but actually we have even longer. But on this chart, it's just systematic observations. And sunspot cycles, sunspot number, it is a kind of characteristic level of solar activity. There are many attempts to predict solar activity with with very different methods, but usually they doesn't work. And the reason for this because we have very limited information for this. In present time, we are very lucky because we have synoptic observations of solar magnetic field. So in this time, we have a solid background to study how magnetic fields evolve. And on this chart, you see combined observations, ground observations from a SOLIS instrument and two NASA space missions, SOHA and SDO. And you see how distribution of magnetic fields with time and latitude, and the black and white colors correspond to different polarity of magnetic fields. And we would like use this data to make more reliable prediction for next solar activity. But of course, we have, it is not such easy just because our knowledge about solar dynamics is very limited. And it is restrict us to make really highly realistic models. In the same time, we have very limited knowledge about observations. What it means, even if you have observations, they cannot give you a vision on a whole picture how solar flows, solar magnetic fields evolve in time. And in same way, our models not able to reproduce in a very realistic way what is going on the sun across whole interiors and surface. And this slide essentially illustrates what if we have some kind of true condition, which we don't know, it is red curve. We have model, it is a black curve there, and some observations. And you see it is discrepancies between all of these. And data assimilation technique, in fact, allows us to make estimation uncertainties both in observations and our models, and correct our model to our correct our model to observations and make understanding of current state of solar activity more precise. And this technique is widely used for prediction of weather, and say you can see what kind of weather will be tomorrow and later. So, but idea is the same. And of course, I'm not going to discuss about these equations, but I would like to give you just a simple overview. We have a dynamo model which describes evolution of global magnetic fields. And of course, it is, even if you have very good technique, it is some very serious requirements to model. We must reproduce with our model general properties of solar activity. On left-hand side, you see, in fact, a few images of which illustrate solar activity. One of them, it is hand-drawn images of sunspots, and we have very long records on this. Importance of such observations because we can calibrate our model and test how it works. But of course, it is the most important to have physical quantities from observations. And thanks to currently available for solar cycle observations of magnetic field, we can do this. And you see just example continuum intensity from HMI instrument at the top and in the bottom solar magnetograms. And these analyses, in fact, allow us, because again, it's still uncertainties, allow us to create a kind of ensemble of models which describe conditions of the sun. And after this, additional analysis, statistical analysis required to find the best, like most correct conditions according to our knowledge. This technique previously was used to predict solar cycle 24, and we used annual sunspot number variations. This prediction was done in 2008, and we are happy to see what this technique works pretty well. And on this chart, the red curve, in fact, corresponds to our forecast, and empty dots, actual observations. And again, because we have limited observational data, we try and first, it is some difficulties how we can combine in this data to predict solar activity. We decided to do separate prediction for each hemisphere using available synoptic magnetograms. And on this slide, you see our forecast for solar cycle 25. And in this plot, in fact, you can see, say, blue curve correspond to our model solution, which is corrected according to observations. Empty dots, it is just not real sunspot number, but sunspot number is estimated from magnetograms. And the red curve and dark green curve just overlapping with the red one is our prediction. And you see, if you compare solar cycle 24 and 25 for both hemispheres, we have significantly weaker amplitude of variations. And this approach, according to our previous experience, work very well for, in most cases, for 8 years ahead, but it potentially can work even longer. how it was shown for cycle 24. And of course, because we made the forecast for each hemisphere, we can discuss about total solar activity. It is presented on this slide. And in context of time evolution of solar activity, you see sunspot number observations records for several hundred years. And you see our prediction for solar cycle 25, in fact, shows what next solar cycle will be will be significantly weaker than current solar cycle with some uncertainties. And probably it will be a weakest solar cycle for last 200 years. And to conclude of this, to understanding solar activity is one of most important problems in our life because we so highly depend from solar activity conditions. And one of way to make a reliable prediction is use a data assimilation approach, where we combine our model which based on our present knowledge and available observational data. And this technique already have been successfully tested for prediction solar cycle 24. And in current time, we use available observations, ground observations from National Solar Observatory and also from two NASA space missions to make a prediction for the next solar cycle. We expect that what solar cycle will be significantly weaker than the current one. And we expect to have extended solar minimum, and solar maximum will happen in 2024, 2025, with probably a double peak of activity. This work was supported by SHINE program, NSF, and thank you for your attention. Thank you.
Launching. So good morning, everyone. I'm reporting this morning on research in progress that was made possible by tens of thousands of citizen scientists who participated in the Milky Way project. The Milky Way project was one of, well, hundreds of research initiatives that have been launched on Zooniverse over the past 10 years. Zooniverse is the world's largest and most popular platform for citizen science. The Milky Way project was about finding sites of recent massive star formation in our galaxy. It was based on using large Spitzer surveys of the inner and outer galaxy, over 300 square degrees, Spitzer images, and these sites of massive star formation. When I talk about massive stars, I mean stars typically more massive than about 8 times the mass of the sun that ionize their surroundings and produce H2 regions. In these Spitzer infrared images, those H2 regions look like the image you see on the left there, sometimes referred to as bubbles. Most of what you see colorized blue is stars, green, organic molecules, and red corresponds to dust. Now, in the course of identifying these sites of massive star formation, our citizen scientists began to tag compact yellow objects, roundish yellow objects that sort of look like the ones nestled between those two large bubbles on the right there. Hashtag yellow balls. The name has stuck. We had good reason to think that these yellow balls might represent infant bubbles, very early stages of the production of these bubbles. So we redesigned the Milky Way project interface to be able to build a catalog of these yellow balls, and during 2016 to 2017, more than 6,000 of these YBs were identified and their angular sizes measured. I won't get into how we discovered the distances, how we calculated the distances very much, but suffice it to say that the angular sizes of these yellow balls actually map on to distant sizes that are sub-parsec in scale, so think light year and smaller. So this is a great example of why yellow balls are particularly interesting to us. With some of these objects, you can peer inside these mid-infrared opaque objects and actually identify young clusters of stars at near-infrared wavelengths. But at the same time, if you look over on the right image there, Atlas Gal, sub-millimeter and millimeter wave observations indicate that most of these yellow balls are actually still embedded in the dense clouds that form these stars. Why is this interesting? This is interesting because in most cases, young clusters of stars destroy their environments pretty quickly. And it's difficult to both see stellar content and the birth clouds at the same time. So these yellow balls give us great hope of actually being able to relate the initial conditions of star formation to the star clusters that are being produced. So we decided to start with a pilot study of a modest 20 square degree region of our galaxy that's well studied between galactic longitude 30 and 40. This is an example of one of the yellow balls in that region. We started with this region because there's a wealth of surveys, both of molecular gas and of young massive stars that we could cross-match with our yellow balls, and we found some interesting things. So one, only a fraction, maybe 20% or so of these yellow balls are associated with known H2 regions, known ultra-compact H2 regions, or massive protostars. But more than 70% are actually very still deeply embedded in their dense gas. So we revisited the question. Initially, we thought YBs might all be very young bubbles. Do all YBs, do we expect them to produce massive stars? And why is this a critical question? Well, of course, the massive stars that sculpt these bubbles eventually explode as supernovae and enrich the interstellar medium with heavy elements. So we would like to understand how massive stars form and how less massive stars form, differences between those two. So in this histogram here, it's a histogram of luminosity. KWA15, the dashed histogram, shows you a sample based on very, very early identifications, a paper we published a few years ago. And the very early sample, this sample has been cross-matched with known massive protostars, and you see that they're pretty high. They're shifted over on the right there to pretty high luminosities. I know you can't read the tick marks. The tick marks above indicate various spectral types of young O and B stars. So the cutoff for stars that will eventually form supernovae is shown by that vertical blue line. Everything to the left of that are lower luminosity objects. So this was really interesting to us for a number of reasons. One, the number of yellow balls or YBs that have been discovered outnumbers bubbles by about a factor of 2. But we expect this stage to be much shorter lived, by about an order of magnitude. So we're looking at a snapshot sort of in time at similar evolutionary states of young star clusters that represent diverse star-forming regions over several orders of magnitude in luminosity, and not shown here, but also in mass. So roughly 1/3 of the yellow balls in our survey are new star-forming regions, in the sense that they don't have analogs in catalogs of young stars. They're circled. This is a 2-color shot that we're just seeing the gas and dust in a 6 square degree region of our galaxy here. Again, not associated with cataloged massive star formation. These yellow balls actually have the characteristics of protostars, which are still in the process of accumulating mass, and also with intermediate mass star-forming regions, those regions that are forming these less massive stars that won't form these full-fledged bubbles. So one of the things that we're in the process of doing now, I told you this is research in process. We want to measure the properties of these yellow balls across the entire catalog in a consistent fashion. So we're working with some Python guru undergraduate students at the College of Idaho that are helping develop a graphic user interface and a catalog interface, so that basically we can perform aperture photometry. We can measure the flux across many different wavelengths of these yellow balls by isolating the yellow ball from its background, like the images in the left panel here. And on the right, you see the background with the yellow ball removed. So we're developing methods of interpolating across the background so we can measure the flux just from the yellow balls. And we're really excited about being able to produce spectral energy distributions, measuring the flux of these objects across many, many different wavelengths. So here's a question that always comes up. Are citizen scientist identifications reliable? Well, some catalog entries are fake yellow balls, and by that I mean they're not the compact star-forming regions of interest to us. They're misidentified mature stars or little bits of fluff in the interstellar medium. Our pilot study suggests that this fraction is small but significant. We're currently in the process of exploring the nature of yellow balls that have absolutely no matches in any of these catalogs, about 14%. We're also doing models of yellow balls to compare their compactness to the user-supplied sizes. We want to, among other things, decide for future Zooniverse projects what is and is not useful for the citizen scientists to measure. The animal-based projects are pretty obvious, right? Citizen scientists can distinguish between animals. Distinguishing between bits of the interstellar medium is a little bit more difficult. So in summary, citizen scientists have discovered more than 6,000 of these yellow balls across the Milky Way. We have very good evidence now that at least most of these are young star-forming regions that span an enormous range in luminosity and mass of their parent clouds. Some host massive stars, many do not. And in many cases, we can actually see embedded star clusters in their birth clouds. So there's the possibility through future observations of linking stellar properties to their actual birth clouds. So if I were to summarize with one sentence why this is really important is now we have the opportunity to compare very young, different environments producing very, very different types of stars. And this will be particularly interesting to observe some of the closer objects at higher resolution with instruments like ALMA that can peer down to the kind of scales where the kernels, where the cores within these larger clumps are actually still assembling matter. And so thank you, and a big shout out thanks to the tens of thousands of you who participated in the Milky Way project. And please check out my poster 201.04 downstairs for more details on how we did a number of these things. Thank you.
Good morning. So we're going to be moving to the dark side now. So I'd like to talk with you today about our dynamical analysis of the Antlia 2 dwarf galaxy, which was recently discovered. And we now believe that this is the dwarf galaxy that crashed into the Milky Way some several hundred million years ago and produced the very large ripples that we see in the outer gas disk of our galaxy. Now, for me, this is somewhat of an old story, which also has a new beginning, one I think that is a happy one. But let me start with the history. So, some 10 years ago, I was a postdoc at Berkeley, and I came to learn about these large perturbations that are manifest in the outer gas disk of the Milky Way. The plot that you see on the left was constructed by Levine, Blitz, and Hylas, and shows the gas density distribution in the outer parts of our galaxy. And as you can see, it's highly non-uniform. There are large splotches, there are spiral structures, there are large perturbations or ripples that are very difficult to explain in a purely isolated context. So at that time, I started doing a couple of things. One, we started developing a new method to hunt for and characterize dark matter-dominated dwarf galaxies from analysis of their gravitational imprints on the outer gas disks of spiral galaxies. And secondly, we made a very specific prediction for how massive the dwarf galaxy would have to be and how close it would have to get to the Milky Way to produce the structures that you actually see in the outer gas disk of our galaxy. The movie that's running shows the gas response on the left and the stars on the right. The top panels show the Milky Way face on, and the bottom panels show the Milky Way edge on as the dwarf galaxy interacts with our galaxy. Now, the reason we had to invoke a new perturber was that we showed that the known tidal players of the Milky Way couldn't do the job on their own. Okay, now, of course, these days we know about many dwarf galaxies that orbit the Milky Way, but there are some that are particularly significant in their tidal strength, and these include the large and small Magellanic Clouds that you see below the plane of the Milky Way, and the Sagittarius dwarf galaxy. This is from a computer simulation that we did some time ago, and what you see here is the guts of the Sagittarius dwarf galaxy have been spewed across the sky as it came too close to the Milky Way and was cannibalized in the process. And this is a new computer simulation that I've done that includes these three tidal players of the Milky Way, the large and small Magellanic Clouds, and the Sagittarius dwarf. And these three alone are not sufficient to do the job. So we had to invoke a new perturber. Now, we are confident that our method to hunt for dark matter-dominated dwarf galaxies does work because we've tested it on galaxies like the Whirlpool galaxy that's shown here. This is the gas density distribution of the Whirlpool galaxy, or M51, which has an optically visible satellite. So in cases like this, we can check if the method works, and in fact we've done that, and so we're confident that we have a robust method to hunt for the darkest galaxies. So here's what's new. So several months ago, there was a dwarf galaxy that was discovered towards the Antlia constellation, now known as Antlia 2, through analysis of Gaia DR2 data release 2 observations. And what you see here on the leftmost panel, my left, is an overdensity of stars. And you can identify the distance from the tip of the red giant branch stars in the color magnitude diagram. And we also have proper motion data, so we know how it's moving. Now, this dwarf galaxy is unique in several ways. It is similar in extent to the Large Magellanic Cloud, which, as far as dwarf galaxies go, is pretty big. So it's a giant dwarf galaxy, if you like, which is an oxymoron. But note that it is 2 magnitudes fainter than the Large Magellanic Cloud. So it's extremely faint for its size. In fact, so much so it is the lowest surface brightness system that we know about. It's also very close to the plane of our galaxy. It's just about 11 degrees from the plane of the galaxy. And it's pretty far away. It's about 130 kiloparsec away, or about 400,000 light years. So, we were very intrigued when we heard about this discovery. And there are several things that stood out to us immediately, even before we'd done really any calculations. One, of course, was the radial location of the recently discovered Antlia 2 dwarf galaxy, which was very, very close to what we'd predicted 10 years ago. Secondly, this dwarf galaxy was clearly on a near coplanar orbit, again, very similar to the now 10-year-old prediction. And finally, while we don't directly observe the dwarf galaxy progenitor or early time mass, we can infer it. And the inference using standard relations gives us about 10 to the 10 solar masses, which is very close to the model that we had earlier. So what I've done here now is I've taken the measured positions and velocities of Antlia 2, and I've calculated its backward trajectory. And I find that on its backward trajectory, it gets quite close to the Milky Way. It gets within 10 kiloparsec of the galactic center, and that is close enough for it to drive and excite these large ripples that you do see in the outer gas disk of our galaxy. So the movie that was running, again, showed the gas response on the left and the stellar response on the right as the Milky Way interacted with the Antlia 2 dwarf galaxy. Here, the orbit is derived from the recently measured Gaia proper motions. Now, this is a different rendering, but it's showing the same thing. The stars are on the top, and the gas response is on the bottom as Antlia 2 interacts with the Milky Way. Now, if this is the dwarf galaxy that we predicted, it means we have very stringent constraints on its mass and on its orbit. So what's left undetermined then is the density profile of dark matter in this dwarf galaxy, which for these very low stellar masses now means that we have an unique laboratory in Antlia 2 to understand the nature of the dark matter particle itself. And in closing, I'll just say we decided to put ourselves out there one last time. The Gaia proper motions have pretty large errors, so we've made a prediction now for the proper motions that this dwarf galaxy should have, if in fact it is the one that we predicted that corresponds to the very low pericenters, and this can be tested in the near future with upcoming Gaia DR3 data. Thanks for your attention.
I'm beginning to regret having recently bought a new solar telescope. Because next solar cycle is going to be even worse than this one. There's hardly ever anything to look at. All right, well, thank you very much to all four of you. Interesting stuff, both locally in our solar system and locally in our galaxy. We're going to take questions now from here in the room, and if you're on the webcast, please queue up your questions for Trey, and he'll relay them to us in a few minutes. Do we have any questions? Please wait for the microphone, which Susanna will bring you, and then tell us who you are and who you're asking your question of, so that the people on the webcast know who's talking. I see one hand up down here in the front.
Jim Small, St. Louis Astronomical Society, and a couple other places. I'm part of a group called Virtual QuarkNet, and we have tons of high schools that have cosmic ray detectors. So this is directed at Robert. We could probably, in our summer group, maybe coordinate some experiments with those detectors to look at levels of cosmic rays and so on. And I'd be very interested in see what you would like us to do.
Go ahead.
Yeah, so I only showed you data from the University of Oulu Observatory in Finland. Different detectors around the globe have slightly different responses based on their latitude and longitude, or magnetic latitude and longitude. So yes, certainly as a follow-up study, one could see just how the response differs at different sites around the globe. So yes, I certainly could think of something that we could. Would you expect our flux to dip in April 2020? Everyone's flux will dip. It's the question is just how. By how much, because of what your sensitivity to just how, depending on where you are on the globe, some things just bounce right off because of the Earth's magnetic fields. But yes, everything will dip and dip sharply. Thank you.
Any more questions here? All right, Andy in the back.
Andrew Fracknoy, textbook author and freelance. This is a question for Grace. Tell us a little bit about the human side of this. When these citizen scientists discovered what seems to be a new phenomenon, were you able to share it with them? Were they excited? Did that help in the vigor with which they pursued the rest
So
of the project?
here I like to quote Isaac Asimov. And now I'd like to misquote Isaac Asimov, paraphrase him. There's a famous quote where he mentions that how odd is music to his ears compared to Eureka, that most new discoveries are heralded by curiosity, by just people who are curious about something. That was the case with these citizen scientists. Zooniverse is great because all of these projects have social media attached to them, so we have talk sites where our citizen scientists interact with us. I was a moderator for the Milky Way project, so they can interact with the team scientists. We have blogs. We let them know what we're up to, how we're doing. We did acknowledge in the very first paper, which was just a quick look at these objects, we acknowledged the top 4 yellow ball participants. But as you know, in some of these cases, the citizen scientists actually get their names on the publications with the scientists. So I think this is great because it gives people not just the opportunity to make a contribution to science, which is the #1 reason why people participate, because they want to do that, but it also takes them through the process. And I think it makes science and scientists a little bit less scary. They get to talk to us, they get to know us, and I think this will come a long way. Citizen science has the potential to bridge a number of the culture wars going on in our society today. Thank you.
Another question?
Curiosity is exactly right.
Yes. Trey, do we have any online?
We do.
Okay.
So Monica Young from Sky and Telescope has a question for Bob. Bob, she's taking your bait. Why was the last solar cycle unusually long?
Because the Halloween storms. Basically, the very large storms in October 2003.
You mean solar storms, right?
Solar storms, yes.
Yeah.
Yes. CMEs, massive eruptions, the biggest flare ever recorded, basically sucked. Think of me paraphrasing The Princess Bride. I've just sucked 1/3 of your cycle away. How do you... This is for posterity, be honest. So, yes, I mean, if you go back and think of my band's picture, that some fraction of flux from that, from the next cycle band got close enough, got sucked into the 10486, and two polarities or two opposite polarity magnetic fields in one sunspot is the recipe for the biggest flares. We call them delta spots. So yes, there was a measure of, because so much of the flux and helicity got sucked out, and I can show you the graph on the poster. I didn't include it in this, but that there's you can think of it as a change in speed of the progression of the cycle. And similar thing happened in late 1960 as well. So which is why the cycle 18 or 19 was somewhat low. So I'm going to respectfully disagree with Irina here, that I actually think that the next cycle is going to be of similar magnitude to the current one, which is still low by historical standards, so we're not talking, catastrophically low. But
we'll come back in 11 years and see how you did.
We will, or in 2023 or 2025, and come back to see when maximum is. But yes, and I'd be happy to follow up on or offline or online with Monica. But yes, there's images downstairs to discuss that. And thank you.
Anything else online?
We do. There's another question for Bob, and this is from Rick Lovett, Science. And how do cosmic rays affect the weather? So what are the exact mechanisms by which cosmic rays and weather interact?
The working hypothesis that we have is that it changes the electrical conductivity of the upper atmosphere. And because at solar minimum the atmosphere is stretched out, that it makes it more receptive to the change in cosmic rays, rather than any change we see in higher activity levels. I will admit that there is the possibility of it's definitely driven by cosmic rays. The other possibility for the intermediary step is it's something to do with ozone and nitrogen oxide chemistry. That some folks in Colorado have this is the so-called sudden stratospheric warming, which is an ample literature. But I guess we will see soon enough as to exactly how it works. Or I can go back and look at 2010, 2011 as well. I just haven't had the time yet. That's a follow-up study. Thank you.
Sorry, there's a little bit of a follow-up on that.
Okay.
So just how much energy, watts per square meter, whatever unit, of energy from cosmic rays actually reach the Earth? And does that vary greatly during the solar cycle? Can you explain how much of a variation there is?
Sure. Well, the graph that I showed from Ulu goes from about 7,000 counts per hour to about 4,000 counts per hour. Remember, it's anti-correlated, so the highest levels are now at minimum, and different sites around the world have different count rates because of where they are. The actual amount of energy deposited is of the order of tenths of a watt per meter squared. So it's not sort of direct heating that we're doing. Yes, the climate folks tend to view all their, express their forcings in terms of watts per meter squared. Like this much CO2 is this much watts per meter squared. But it's there's clearly some amplification mechanism that shifts. It's the shifting of clouds is what ultimately controls things, and how are those clouds seeded, either directly by cosmic rays or by ozone chemistry.
Okay. Any more questions here in the room? I have a couple. I guess I'll stick with Bob for a second, just because we're in that groove. When you were talking about how you need global warming, climate change to make this system that you're using work, I wondered if paradoxically that means that the fact that we're experiencing climate change and global warming is actually making it easier for you to predict the solar cycle.
It's not making it easier to predict the solar cycle. It is definitely making it easier to predict the consequences on Earth. Yes, absolutely. So the data I showed is from 1960 or thereabouts onwards, which is right at the start of it. If you look at the so-called hockey stick graph of temperatures, when that the monotonic rise in temperatures kicked off. So going back to look earlier, I see this, the correlation is there for the weaker solar cycles around 100 years ago, and then it kind of sort of goes away a bit in the 30s and World War II era. But then from the 50s, when we see this, the monotonic rise in temperature due to whatever, well, we know the rise in temperature, but there's this kind of lump around World War II that is probably due to, not due to the fact there was conflict, there's just the decadal scale atmospheric and ocean turnovers. led to things sort of breaking up. Since 1960, this has been coherent for 5 solar cycles. So, yes, in terms of predicting disasters and mitigating, yes, there might be a silver lining to a very dark cloud.
Then I have a quick question for Grace as well. So what role, if any, do you think the James Webb Space Telescope will have in helping you, dissect what's going on inside these yellow balls? You mentioned ALMA for follow-up, but I don't recall you mentioning Webb.
Right, I didn't, because I'm thinking about so the James Webb Space Telescope will be able to, I think, elucidate some of the stellar content of these yellow balls. What I'm particularly interested in studying the dynamics of the gas, because some of these objects are definitely protostellar in nature. They're still accreting a lot of material. So I'm particularly interested in the studies of the long wavelength. I have to admit, I haven't thought that much about James Webb right now. We're still in the process of crunching a lot of data.
So you need
so
to
we'll have a better
far-infrared
idea
submillimeter type.
when we see when we choose a subset of these objects that look like they have interesting stellar content. Yes, absolutely. I think that those would be particularly interesting to study at near-infrared wavelengths with James Webb, and would tell us a lot about the types of stars. Thank you.
Okay, very good. Well, we're at the top of the hour, so I think we'll wrap it up. I want to thank our speakers again for their presentations. And I want to thank the audience, both here and online, for tuning in. We have one final briefing, which is this afternoon at 3 p.m. Central Time on cold quasars and hot cosmology, so I hope to see you back here in 3 hours. Thank you all very much.